Hello, students. In this video, I want to talk a little bit about the friction on a between a block and the surface of an inclined plane. So what we have here, we have a block that is resting. This block with mass m here is resting on this inclined plane. They have an angle zeta, right, respect the horizontal. So which are the forces if we don't apply any external force that are acting on this block? We have just the weight, of course, right? That is the product of the mass of the block times the gravity. And doesn't matter that the plane is an inclined plane, the weight will be pointing downwards because always point toward the direction of the center of the earth. And then we have the normal force. And if you remember the previous video that I show you, in that case, the normal force was in the same direction. That means was vertical as well was the weight because we have a flat surface. But now the normal force is not in the direction or it's not vertical as the weight is. And why? Because the normal force, as its name means, right, is a force that is always acting perpendicular to the surface where the object, is just resting. So when we now analyze the components of the weight acting here, we can break the weight into components. We have one component that will be perpendicular, that will be perpendicular to the surface of the plane, so I will call this component W perpendicular. We can represent perpendicular better with the symbol of perpendicular. And we're going to have another component that will be parallel to the surface. So it's going to be like this, right? So this is the parallel component of the weight. So now, if the angle theta we have here between the inclined plane and the flat surface, the mains and the horizontal is theta, that will be also the angle between the weight and its component that is perpendicular to the plane. So this here will be your angle theta. So now if we calculate, right, in this case, the magnitude of y of W perpendicular, I mean the perpendicular component of the weight and the magnitude of the parallel component of the weight, and if we assume that we have here a triangle, that is going to be a right triangle, right? So this W perpendicular, the perpendicular component of the weight would be adjacent side to angle zeta. So we have that W perpendicular will be equals to W cosine of theta, right? Or we can say this equation is coming from cosine of theta that is equal to adjacent over hypotenuse, right? It would be W perpendicular over W. So when you solve for W perpendicular, you get that W perpendicular is W cosine of theta. So if I know that W is mass times gravity, now I know that W perpendicular is mass gravity cosine of theta. If now I want to find the parallel component, right? The parallel component, I know that the parallel component, W parallel, would be W sine of theta. Why? Because this is coming from sine of theta equals the opposite side to the angle theta. That would be this segment we have here, that is parallel to W parallel So it's the same, the W parallel, so it will be W parallel, the parallel component of the weight over the weight, right? So if we know that weight is mass times gravity, now we know that the parallel component of the weight is mass gravity sine of theta. So what it means that if now we have a block here that have a mass of, suppose, uh, 2 kilograms, right? And we have that the coefficient of static friction between the surface, right? Uh, the surfaces, right, is equal to, let me say, 0.5, and let me say that the coefficient of kinetic friction is equal to 0.2, and let me say that the angle theta is equal to 20 degree, right? I want to find out, right, if this block is at rest, if this block that I have here is at rest, uh, that means I am holding the block, so it's at rest. If I release the block, I want to know if this block is going to slide down or not. The question here is if it's going to slide down or not. So what happens, what is the condition here? The only way that this block is going to slide down, right, is if, as you now are going to see, as we have here, this W parallel. This W parallel would be the force that is going to make the block to slide down. But of course, as we have a surface that is not a frictionless surface, right, we have a force of friction here that is static because we have the block at rest. So the only way that this block slide down is if the parallel component of the weight is greater than the force of static friction. If the parallel component of the weight is greater than the force of static friction, this is going to slide down. Why the parallel component of the weight, that is basically the force that is pulling down this block, be lower than the force or equal to the force of static friction, the block is going to stay at its position. So I want to know if this is slide down or not. What I have to do, I have to first find W parallel. So I know W parallel, the parallel component of the weight. And when I say parallel, remember that means parallel to the surface of the incline is mass gravity sine of the angle. So it would be 2 kilograms times 10 meters per square seconds times the sine of 20 degree. So W parallel would be 20 newtons sine of 20 degree that we said there is the angle. So let me pick a calculator now from mine. So we have now sine of 20 degree that is equal to 0.342 times 20. This is 6.84 newtons. This is 6.84 newtons. Now, what about the force of static friction? The force of static friction depends on the coefficient of static friction and the normal force. So if I want to find now the force of static friction, I have to find first, the normal force. So I know that the normal force, we have the same magnitude that the parallel component of the weight, right? So in magnitude, the normal force is equal to the perpendicular component of the weight. So it's going to be equal to W perpendicular. So it's going to be equal to mass gravity cosine of theta. So it's going to be equal to 2 kilograms times 10 meters per square second times the cosine of 20 degree. So knowing this, if I do my calculation now, I know that uh, the normal force is equal to 20 newtons cosine of 20 degree. So the normal force is cosine of 20, what is 0 0.939692.6, okay, times 20 is equal to 18.79. So the normal force is equal to 18.79 newtons, or 18.8 newtons, right? And then now, once I know this normal force, I can find now the force of static friction. So I can say that the force of friction static is equal to mu static, the coefficient of static friction, times the normal force. So this coefficient of static friction, we said that is 0.5 times. Remember that the coefficient of friction doesn't have any dimension, right? So doesn't have units, so it's just 0.5, and 0.5 times the normal force, that is 18.79 newtons. So we're gonna have that this is equal to sorry. So multiply times 0.5, it would be 9.39, I mean 9.40, 9.40 newtons. So what we have here, we have basically, let me move this a little bit. So we have our block here. There is a force like this, that is the parallel component of the weight, equal to 6.84 newtons. And there is a force like this one, that is the force of friction, that have a magnitude of 9.40 newtons. So in front of the question, if this block is gonna slide down the incline, we can say that no, because the force of friction is still greater than the force that is going to make this block to slide down. There is basically the parallel component of the weight. Because there is no external force here, that means you are not pushing the block with your hand, you are not pulling the block, using a rope or a string. You are just putting the block on the surface, on the inclined surface, and you want to see what happens, if it's going to slide down or not, right? Uh, how can we make this block to slide down if we increase the magnitude of the angle theta? If you increase the magnitude of the angle theta, eventually this parallel component would be greater than the force of static friction. So the force of static friction is not going to change at all. Why? Because it depends on the normal. The normal depends on the mass, because it depends on the weight of the block, and the weight of the block depends on the mass, right? So, well, the force of static friction, if we change the angle, is going to change, because the perpendicular component is going to change, really. So it's going to change. But what is going to happen with this is that perpendicular component will turn lower. So the force of static friction will turn lower, while the parallel force will turn greater. So let me show you. This very interesting thing. So let us think now that the angle, instead of 20 degree, suppose that we increase the angle theta to 40 degree. So if we use 40 degree, this would be sine of 40 degree. And if we use sine of 40 degree, we have sine of 40, sine of 40 times 20, should be 12.86. So this value will be now 12.86 newtons, right? And now we are going to replace this angle by 40. So this would be replacing this by 40. Remember, we're going to replace this by 40 degrees. So we're going to see what is the new value of the normal force. So we have cosine of 40, that is 0.766 times, 20. This would be 15.32. And if now we replace this value of normal force by 15.32 and we multiply them by zero point 0.5, that is the coefficient of static friction, this value now turns into 7.6 newtons, or 66 newtons, approximately 7.7 newtons. So what happens now? Look at this. You have a force parallel, you know, of 12.86. So this force now is 12.86 newtons. And we have now a force of friction that will be 7.66 newtons. So now this force is greater than the force of friction, so it's going to slide down. So changing the magnitude of the angle theta, these have a double effect. If we increase the angle theta, there would be a lower value of the force of static friction because there is a decrease in the magnitude of the normal force, and there would be an increase, in the magnitude of the parallel component of the weight. So that is the force that is going to make this block slide down. So if now you want to find, of course, for any of these scenarios, the force of kinetic friction acting there. So once the block is moving, what is the force needed, to keep the block moving? Just calculate the force of kinetic friction. How do you find the force of kinetic friction? Instead of using here mu sub f, you mu sub k, so you use the coefficient of kinetic friction, and that would be enough then to find the force of friction there, the force of kinetic friction there. So I hope the video, was interesting and help you to understand better this topic.